Alright, our next topic is conical pendulum. So conical pendulum is when you have a mass swinging in uniform circular motion on the end of a swing. And we set this up and we call this a conical pendulum. Now I'm not sure how great that video is, but I'll try and draw it for you instead. And so the idea is that here we have this string connected down to a mass of weight m, and the mass is swinging in a circle. And because it's in uniform circular motion, then horizontally the forces acting on it must add up to mr omega squared. And vertically the forces acting on it, because it would be swinging in a horizontal plane, the forces acting on it would be equivalent to mg, so they'll equal mg. Now the forces will come from this string, from the tension in the string, the tension force there. And so if we resolve that force there, and if we say that the angle made here at the apex is theta, then this force along here, the horizontal force, will be equal to t sine theta. That will be the horizontal component of that tension. The vertical component of the tension will be given by t cos theta. So what we want to do with conical pendulums is we want to resolve the forces both vertically and horizontally. Now to get a little bit more information about this, we can combine these to eliminate t and to get information about theta. So we can take this as equation 1 and equation 2 and we can divide them. 1 divided by 2. And that'll give me t sine theta over t cos theta. And that's a nice way to eliminate t. I get mr omega squared over mg. The t's cancel and sine on cos is tan. So I get tan theta is equal to r omega squared on g. And if you have a look at that, you notice that what's happened here is that the angle of the rotation at the top is actually independent of the mass. The mass doesn't matter here. The m's cancelled out. Now coming back up here, if we said that this was r, this was h, and this was l up here on the diagram, then I can have a look at that and I can see that tan theta is the radius over height. So I can say tan theta equals r on h, but I just found out that tan theta was r omega squared on g. So now I can get formulas relating this. R on h is equal to r omega squared on g, and if I get rid of the r's, bring the g across, I get omega squared is equal to g on h, or omega must be equal to the square root of g on h. So I can see from that that I actually have a relationship between the angular velocity, gravity, and the height. Now the period of motion, it'll be a 2 pi will be the angle it passes through, and it'll pass at omega is the velocity, so we'll get 2 pi over omega, flip that upside down, h on g, square root of h on g is the period of motion. So we've got these equations starting to form, but we've got another one here as well. We've got this t sine theta equals mr omega squared. So t sine theta equals mr omega squared. So further, and coming back to my diagram, if I know the length of string for my pendulum, then I can see here that sine theta is opposite over hypotenuse. So I can say that sine theta is equal to r on l, or in other words, r is equal to l sine theta. And substituting that in here means I can eliminate theta from the equation, and I can get t is equal to m l omega squared, with r being l sine theta and the sine theta is cancelling out from both sides. That's a useful equation to remember. That's useful to remember that if the pendulum is in a uniform circular motion, the horizontal component of this tension force must be mr omega squared, must be equivalent to that. If the pendulum's not bobbing up and down, if it's staying in a plane, then the vertical component of the tension force must be equal to mg, the vertical force acting on that mass. Division gives me a formula for tan theta, and taking a little bit further, I can actually get a formula linking omega g and h. Period of motion, and then further this one down here.